So, second half of classification tonight, looking at actually predicting our 20 news groups now. So we sort of ended here with like, how do I determine what makes my model any good? Right? And I have this model, is it worth anything? And we were really looking at confusion matrices when we ended last time. So confusion matrices are a really good way to think about model predicted categories, because these overall statistics for the model may not tell you anything useful about the actual predictions. So sure, I can calculate all of these numbers for my overall model, but if one group is way larger than another group, I will mistakenly believe that I have an accurate model, although really what's happening is we're predicting the larger group really well and we're not predicting the smaller group at all. So we want to either look at a confusion matrix or calculate these statistics by group, which is essentially many, M-A-N-Y, M-I-N-I, many small confusion matrices. Okay. So what they tell me is the predicted label, so let's say the atheism subgroup, versus everybody else. So when you don't have a two-category problem, it's not, this group versus that group, it's this group versus everybody else. And it's a really great way to see where your model is getting it right and wrong, because then you might have some better ideas on what to do to get them more right. So let's look at the confusion matrices picture here, because I think this just really hopefully makes it pretty clear, right? So confusion matrix has the actual, if I'm omniscient and I know the actual real answer, okay, to the experiment, where this is a positive, this is a yes for that group and a no for the other groups, right? So yes, atheism, no, everything else. You can also think about this in medicine. It's a little bit easier, a positive test versus a negative test. My model predicted value, right? So positive for the prediction and a negative for the prediction. So each square has a name. And a true positive is when we predict that it's positive and it actually is. Okay. Sometimes this is called a correct rejection. Correct rejection. No, I'm sorry. Power. If we're going to talk about statistics, right? Comparing the statistics, this is sometimes called getting it right, right? Or in stats, power to find the effect if it's there. If it's actually negative and I say it's positive, it's called false positive. Sometimes called a false alarm when you say something's true and it's not. In statistics terms, this is alpha, right? The probability of making a type 1 error. Okay, so that's one way we're looking at is across here. For our other statistic, we're going to look down this way, right? So it's actually positive, but our model predicts it's negative. It's called a false negative. Okay, this is a miss, where it should have found the thing, made it positive, right? But it's not. And in statistics terms, this one's beta. So type 2 error, we missed the effect that's there. And this one's called a correct rejection. I got backwards there for a second. When it's actually negative and we predicted it negative, a true negative. Not a whole lot in machine learning terms deals with true negatives, right? They're mostly interested in this true positive ratio versus false positives and true positives versus false negatives. Okay. Now, in medicine, they're interested in these true negatives. Okay. In statistics, we're just sad, right? Because there's no effect there, and we correctly said there's no effect. But in medicine, negative predictive value is actually pretty important, right? So knowing that when you get a negative test that it actually is negative. But in our case, negative is just the other category. So we're really going to focus in on the true positive ratios. And so this is just them spelled out if you need it again later, but a true positive is an incident where the target category is indicated, and it's actually that target category. Okay, so we predicted it was sports, and it actually was supposed to be sports. So this is why you can see you have to have the right answer to calculate these statistics. A false positive is when we predicted it's the target category, but it's not. It's something else. Okay, and we can be false in many ways. In our example, 19 other ways. True negative is where the target category is not indicated, and it's not the target category, so again, we're getting it right. And a false negative is where it's not indicated and it should have been. It is the target category. So it's a miss. Now, what can I do with those? Well, from those true positives and false negatives, we can actually calculate performance. And this is one of the only times you'll see the true negatives show up. Okay, true positives, true negatives, those are both correct answers, divided by the total number of answers. So this is the very basic definition of accuracy, where it's the overall proportion correct prediction from the model. Usually that one's not too hard. Precision is a ratio of positive values, so sometimes called positive predictive value, where it's the number of times you're right for the positive class given the number of false positives. So it's true positives divided by true positives plus false positives. So given that you guessed the positive class, how many times were you right? Recall is kind of sometimes called sensitivity in more medical-based fields, but it's the percent of true positives that you actually captured. So given that you are looking at the ones you were supposed to mark as positive, how many did you get right? Okay, so it's true positives divided by true positives plus false negatives. So one more time, the distinction. Precision is the number of times you actually guessed positive. How many times did you get it right? Versus the number of times it was supposed to be positive. How many times did you get it right? And that distinction is really in the denominator. Note that these two denominators are pretty different, right? So the false negatives number may or may not be even related, the same, close to a numeric value to the brain fart. False positives, okay? Obviously true positives stay the same. So if we wanted to create an overall score, what we do is create this F1 score. And it's a harmonic mean of precision or recall, but we can't just average them together because they have different denominators. So here's our fancy formula: 2 times precision times recall divided by precision plus recall. Okay, so we'll weight the category with more data. All right, so back to this processing pipeline. First, we're going to import our packages for our chosen algorithm. Okay. Then we're going to create a blank model, okay, what we have down here. We're going to fit the data to the model using the training data that we have extracted some set of features from. Then, okay, so we've worked through the top here, right? We've got our training documents that we've normalized and extracted our features from. We're going to fit it to the data. Using that model, we'll predict our testing data and see how well we did it right by calculating model performance. So that should bring it together all these topics that we've talked about. And then I put my favorite picture back up here. So we'll work our way through the top and then back through the bottom. So let's look at that. Using what we're going to start with is the bag of words method. Okay. So bag of words method, remember, is just a term by document matrix where we are counting the number of times each of the vocabulary terms, which are just here, we're going to use in grams or 1 grams. So each individual token or word, the number of times each word appears in our document. Remember that we have cleaned this document already. We saw that in our previous lecture, where we took out all the stop words and did stimming and all that kind of stuff. Okay. So we won't have the word the drowning out everything in our model. But bag of words, the vocabulary, right, the words that are left, counted inside the cells for each document. So document 1 has 7 instances of the word hockey, for example. Document 2 has 18 instances of hockey. Document 3 has none, that kind of thing. The count vectorizer function in scikit-learn allows us to take this process text and transform it into this term by document matrix. I looked into changing this over to Gensem, which is one of my favorite packages, but honestly, scikit-learn's version of handling these simple matrices is really quite nice, except for one little thing. So I'll tell you the one little thing when we get there. So what we're going to do though is we'll keep using it. I kind of waffled back and forth and then stuck with it. So import, right? Count vectorizer. It's really long. It's like hidden 8 layers deep in scikit-learn. Right, so it's feature extraction.txt import count vectorizer. This actually is no longer necessary. I took this part out because it takes a long time to run. But if you wanted to do cross-validation, there is a function in scikit-learn called cross-val score that will allow you to do some leave in out methods and some cross-validation. So first thing, set up a blank model. Okay, our blank feature model is we're just going to call it CV for count vectorizer. First argument here, binary equals false. This is set to make it actual counts. If you wanted a one-hot encoding, where it's just, is it there, is it not, you could change this to true. Okay, if you're used to R, remember this is proper case, so it's just capital T, lowercase, rest of true. Okay. I don't tend to use one-hot encoding because I feel like it loses the extra data on the number of times a word has been used, but that is something that you can try. So the nice thing about all of these methods is we can pick 3 different extraction methods and pick 3 different algorithms, which is what we're going to do, and run them all. So that's 9, 3 times 3. And see which one gives us the best fit. So it's very easy here to switch from one-hot encoding to not, but we're going to leave it as not. Our min df here is the min proportion that the words have to occur to be included. Okay. So if you want to cut out very idiosyncratic words, meaning they don't occur very often, you could change this number to like 0.05 or something. Okay. Don't go too high because then you're going to lose everything but all the very, very common words. And what you're going to see then is that everything is super related and it may not be predicted. The maximum proportion can be obviously up to 1. And this is where you could tone down a model. Let's say you had a bunch of words that occur in nearly every document because of what you're doing. You could slowly lower this number to eliminate words that are uninformative because they occur too many times. Now this decode error equals replace, this will help with some of the problems that you have when there are bad bytes. So there's these little, I don't even know what to call them other than bad bytes. These little encodings sometimes in our text that this will get upset about. And so if you tell it to replace them, it gets less upset. Now, there are many more arguments for count vectorizer, but most of the ones that we want are the defaults. But I highly encourage looking at their documentation because it's actually quite good, and you can see if there are other parameters that you'd like to tweak. On all of these feature extraction methods, I'm going to give you some basic starting parameters, but do know you could run this model where you change the upper and lower proportion required until you find the right spot. Okay. So one problem that you can have with this type of work is that there are many places to tune the model, and so you could be running thousands of these to find the one that predicts best. Okay. But right now, let's just see if we can find which combination of feature extraction and machine learning math predicts best. All right, so blank model. Next thing you do is you take that blank model, CV, and the function is fit transform. Okay. You run that the first time, and what it does is it takes the corpus. Our training corpus is our giant normalized data set. So it takes that corpus, excuse me, of all of our documents, grabs the vocabulary, right, finds all the unique tokens, and just creates this tokens by documents matrix. Okay, and it's got all the counts in it. So we're transforming the data from a bunch of text to tokens by documents. Cool. Where was I going with this? This is essentially like creating a giant crosstabs, if you're familiar with SPSS, but a double table, right? A conditionalized table. Now for the test features, what you do is actually just transform. So I want to highlight this code right here. Don't do fit transform, because then the matrices are not the same. Okay. So when you train a model, right, fit transform creates the vocabulary. If there are new vocabulary words in the testing data, those get lost, okay, because it's never seen those before. So this is why it's really important to have a large representative training corpus. And so the transform part of the code here makes it the same size. That's vocabulary size. Obviously, it doesn't have the same number of documents, but same vocabulary size as the first one. And if you make this mistake where you run the wrong one, as I have done, what'll happen is that your model won't run. It'll tell you the incorrect number of dimensions. And so you need your training features to have the same dimensions as your testing features. And it's the second dimension that matters. And so I tried to print out a couple of these just to show you that they're kind of weird objects here in Python. So it's a sparse matrix. I've talked about that before. Sparse matrix in like theoretical practical terms is the fact that there are many zeros in this matrix. So not every vocabulary word is in every document, and that creates a matrix with a lot of holes in it. In computational terms, this from NumPy is just an efficient way to store a lot of data. So it's a special type of object that helps us keep from taking up too much memory. Now down here we just did some fancy code to print .shape here. So the first, our training data set has about 15,000 training documents and 71,000 unique tokens. The test data set has 3,700 documents, but the same number of tokens. Okay. And that's the key part. The second feature of the shape needs to match. I've been calling this a term by document matrix because that's kind of the way I've learned it. But I think in this case, it's shaped as documents by terms. It does not really, because practically we're using all of those X columns to predict our category labels, but it doesn't really matter. The idea is the same, right? We have each document and how many times each word occurred in each document. Now, that's our first feature extraction method, and then we're going to build on that idea some more later. The first algorithm we're going to use is log. Okay, I'm positive that many of you are very familiar with logistic regression. I'll give you the very brief one too on it. Okay, it is exceedingly popular. You know, when all this, like, everybody's obsessed with machine learning right now, and like as a statistician, I'm always just like, it's just binary math. Like, it's okay, yes, it's very fancy. So the other day we were talking about writing a grant and looking at migraines. This is a group that I work with. It's a lot of fun. And so the grant that call for grants was talking about the newest machine learning and natural language processing techniques. I was like, they probably mean log regression. Because somebody else was like, what does you teach that stuff? What does that mean? I was like, who knows, right? But because there's so many different things that one can do, and these fields all kind of overlap. So log is a very popular type of math for classification scenarios. So the basic idea behind log in a binary scenario with yes, no, right, is looking here. The left side is our linear regression. We have y is either no or yes. So no down here or yes up here. And we could fit a straight line to this. It's not very representative of the data, but that's essentially what a t-test is. Right? It tells me the group differences on whatever x is between those two categories. Okay? And these are beautifully split. Right? Most data is not this clean. Where one group has a lower score, or the other group has a higher score on x here. Okay, this is t. Instead, with a logistic regression, what we do is instead fit the logit here to it, and we get these S-shaped or sigmoid curves that essentially determine the cut point, the place on which it goes from being group 1 to group 2 here. So where's the 50-50 probability of it being group 1 versus group 2? Okay. Item response theory does a lot of cool stuff this way. Well, basically it allows you to classify, okay, everybody down here is group no, and everybody up here is group yes. Okay. So I can move up into multinomial regression when I have multiple outcomes. And it kind of depends on which algorithm, which version of log you pick, but basically it calculates the likelihood of each group and then picks the one that is the most probable. So if you have one that's like 35% group 1, 33% group 2, 32% group 3, it'll pick group 1, even though those are pretty much you don't know. So that's why I will say it's really interesting sometimes too to look at the probabilities. They are there in the output. Most people just look at the classification label, but sometimes the probabilities are really informative because you can tell if you're getting it wrong by a little or getting it wrong by a lot. All right, transforms linear regression into the logit. Okay. And so each category is classified by looking at those predicted probabilities. And we can create the odds of being in one group over another. Right. Now that's probably more on this slide than it takes to run it. Okay. So two things here. We're going to import logistic regression as one of our functions and classification report because it is great. This is some beautiful coding here. Same rules apply as our feature extraction. Build a blank model, fit the data to it. So we're building a blank log model. These are kind of basic defaults. It does have a penalty marker. I think that's L2. Okay. A solver for how it comes up with a solution. The multi-class option, because we have more than two. Okay. This is the one I usually end up having to tweak. So always watch your models. If they say that they reached max iteration and didn't converge, sometimes they'll still give you an answer. It's usually not a good solution, so you should turn up the number of iterations. Okay. Then everybody's favorite random state is 42, your hitchhiker's joke. Okay. So basic defaults, nothing fancy. Let's fit the model. So log regression dot fit. Okay. You put in whatever x is. So our x variables are our training features that we've already built from account vectorizer. And then y, what I'm predicting, which is their training level label names. When you do this fit, it'll print out what kind of model you were fitting. But once you fit that model, you're off to the races, right? So in normal statistics, I would start looking at like R squared and which predictor is useful. But in this case, we have 71,000 predictors. So maybe that's not the most useful. Now, I probably could pull out which words were the most distinctive, right? And which words have no good prediction. But that's a lot. So instead, most people focus on the actual classification report that you can see down here at the bottom. So we do log regression.predict this time, and we put in our test features. And let's see what happens. So we'll print out our classification report with our test label names, the right answer, comma, the predicted answer. I think you can actually switch these. It doesn't matter because it's still comparing one to the other. Now, I will tell you, classification report, if you don't tell it to print using the print command in Python, it does not print this pretty. Okay? There's the way it's done, you need to put print around it. Okay? In Python, if you run several commands that are supposed to put out output, it will, in general, only print the last one. I think using Markdown, it will actually print most of them, but like in a Jupyter notebook, right? I know that it just will only print the one you tell it to print or the last command. But even if this is the last one, use the print one. It cleans up much nicer. It makes this nice table format. So what's in this table? What can I learn from it? Well, if I come down to the bottom, I get my overall accuracy. It's 70%. Okay. Then I also get the sort of averaged all together precision, recall, and F1 score. So we're going to hold on to 70% as our accuracy for this model. But then I can really dig in, right? So I can look at each category to tell which categories I'm predicting the best and which categories I'm not predicting so well. Like right away, I can tell that the talk, religion, miscellaneous, I'm not doing so hot. I'm doing good at science, medical, but not so good at this religion one. Everything else is in the 60s to 80% range. Now, I do think there's not a misunderstanding, that's not quite the right word. I think there are so many times that we're looking at these values and everybody has in their head that the gold standard is that you have to be like pretty much at 95% or 98%. And I would say that when it comes to the correct scoriness, right? So how well does my model need to do to be useful? You need to think about how many categories there are. Okay? Business-wise, is it actually helpful as well? But first, let's say I'm just trying to predict these. Okay, I have 20 of them. So chance, just random guessing, should get me 1 out of 20. Especially because they're fairly evenly distributed. We have the least number of examples of this one, so that might be one of the reasons why we're predicting it the least well. But, 1 out of 20, what does that math out to, right? 5%. Right? And I am getting 70% right. So I'm doing pretty good. And so I think if there's a gold standard in the field already, obviously you would like to achieve that or higher. But always remember that it depends on the task. That's my answer to everything. Should I STEM? Depends. Right? Should I spell check? It depends. What is a good precision and accuracy score? It depends. I'm the best statistician. It depends, okay? And here, I would say 70% is doing pretty well. Now, if I was trying to do part of speech tagging, those part of speech taggers get into the 95% pretty well. So if we're not getting up there in the 90%, the model's not very good. Okay. Now, if I'm doing part of speech tagging on, let's say, Reddit chat speech, and I'm in the 80%, I'm probably doing pretty well. So, it depends on the task. Okay, that's enough of it depends. You guys get the idea. Let's see what else we might try. So let's switch and do naive Bayes. So I'm gonna leave the feature extraction the same and do a different algorithm. So the way naive Bayes works, and I stole this from the NLTK book, is it has a calculator that first looks at the data, the training data, and calculates the prior probability of each category. Okay. Anytime you see the word Bayes, priors is gonna come up. Okay. Bayes love their priors. This is something that we do intuitively as people, right? So let's say that you are going to lunch with a friend, which we might be able to do again soon, fingers crossed, right? And they're late to everything. So if they're 5 minutes late, because of these prior probabilities on your previous life experiences, you don't, whatever. You just wait. A different day, you're meeting your mom. Your mom is never late. Never. So when she's late, you're probably giving her a call. Like, hey, you're never late to anything. Why are you late? Is everything okay? So naturally, we use these prior probabilities. So why not use what we know about the data? So it calculates the prior probabilities. Okay, and in this example from an LTK, it's got sports, murder mysteries, not motor, and automotive. And so the automotive category is just naturally larger. So we should weight our predictions towards the naturally larger category. Then the likelihood, the conditional likelihood of each feature is added. Okay. So what is the probability, the little mini probability of this feature given the label? So given the word football, what's the probability, right, of that label? I'm sorry, given the feature football, what's the probability of seeing that in each label? Well, sports is going to be much higher than automotive. And it does that across all of the labels. Okay, so that each of those feature contribution, that's the word I'm going for, is added to our category prediction. So it multiplies prior probabilities plus the embedded probabilities of our words given each group. Okay. And then it just, adds them all up. Okay. Then what we end up with is the posterior distribution, which is the probability of our labels given each of these features. Or the conjoint, I think, probability of features and labels. Either way, given this document with all of these features, which label should it be? Is basically the answer. Let's look at that in Python. Very easy. Multinomial naive Bayes. First rule, set up a blank model. Then fit your model. Right, dot fit. So this is one reason why I like scikit-learn, is because the setup to test this is like pretty much the same all the way through. It's very consistent, nicely programmed. Okay. Train features, train label names. Do dot predict. So we did dot fit, now dot predict, and then our classification report. And hopefully what you'll see is overall accuracy pretty much the same. We get 1% extra by using naive Bayes. Okay. Is that 1% a lot? I don't know. But I can see right away that this religion one is still really hard. But also now, in this particular one, for comparison purposes, the atheism one's not doing that great either. Okay. Or the Christian one. So in the naive Bayes one, there is a bit of a pattern here where the religion ones are the lowest, right? And then everything else is in the kind of middle 60 to 80% range. And we actually get like motorcycles and baseball the highest, but we really should look at this F1 score out here, right? So there's something particular that this model isn't capturing about the religion groups in comparison to the other model. All right, one more algorithm. Let's do support vector machines, the linear version. And so what this does is create, we've got our cute super separated categories here in multidimensional space, and we try to create a separating plane, hyperplane, right? That gives us the best categorization ratios, right? So the black line here clearly separates the stars and the triangles. Orange line doesn't get it quite right. The blue line doesn't get it quite right, but the black line gets it really right. Okay. So it finds that hyperplane. The support vectors are these data points that are the closest to the hyperplane. Everybody else who's far away from the hyperplane are easy to distinguish. They're very far apart. What is it about these that are close together? What can we capture that helps us separate our two groups? Because these are the ones that are the most similar. So what's that small distinction that we can hang on to get it right more often? And so our hyperplane is our decision plane that makes these categories separate. And our support vectors are the ones that really help us distinguish, which is a very broad overview of SVM. Okay. Also easy to implement in scikit-learn. So import linear SVC, okay, which is, I don't understand. It's in the SVM section, but linear SVC. And there are curvilinear options. There are other versions. We're just going to stick with some simple stuff today, but there are many other parameters here. Same thing, blank model. Okay. dot fit, and here we go. So here's a convergence warning. Okay. I did not give this enough iterations, but notice that it will still give us an answer. Okay. So what I should do is go through here and figure out how do I update the number of iterations. It's probably max iteration because this is still scikit-learn, but we can look it up here. So linear SVC iterations scikit-learn. It'll give you a chance, or me a chance to show you how beautiful their documentation is. It's so great. All right, loss, blah, 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 multi-class, blah, blah, blah. So it has actually many of the same embedded options in as logistic here. Max iter. Okay, the default is 1,000. I recoded this document so that it should run in a somewhat reasonable amount of time, but let's see if we can make it happier. Maybe, maybe not. Okay, naive Bayes, SVM here. Let's do 10,000. 10, 1, 2, 3. Hit knit. See what blows up. It's going to show me anything. Knit, knit. There it goes. While that's thinking, because my Windows machine can be kind of slow, we'll walk through the answer and we'll see if it'll pop up and make it go away. But this is what you want to look for. Okay, is this kind of convergence warning. We shouldn't put a whole lot of stock in models that don't converge. That being said, let's look at the output and see. And it's not actually probably too far off. It just needs a couple more iterations because it's very similar to our previous models, but it's not as good. Okay. So it is slightly less accurate than our other two models. And, you know, the religion categories are kind of low. Where's that other one? So we've got atheism at the top here in the 50s. Here. This one's 65, this one's 41. Gives us approximately the same pattern we've been seeing before. So which model should I pick? Well, right now, naive Bayes with count vectorizers at 71%, so it's winning. Now, are they that different? No, but I'm still going to pick the one with the best accuracy score. Okay. And it's still hovering in the 70s, which is pretty good considering our number of categories. Okay. But maybe instead of manipulating the algorithm, because clearly math gives us a slightly different answer, can we do something better to the feature selection? And my argument is, I don't know, let's see. Okay. So we're going to switch now to a tfidf, remote term frequency inverse document frequency. It's a weighting scheme that essentially changes those counts into an importance score that sort of normalizes given how frequent that word is and how many words there are in documents. Okay. It lessens the importance of very frequent words, and it actually sometimes will increase the importance of the infrequent words. Okay. Just kind of depends. Now, this is the reason why some people don't like scikit-learn. Okay. The mathematical formula for tfidf, there's actually several different ones. A thing I did not know until several years ago. I learned the one, and like moved on with my life. But there's actually a few different ways to kind of do this normalization procedure. And there is a very long documentation argument over why they're doing the one they're doing. One issue that one can have is that the denominator in this normalization can be 0, which is no good mathematically. And so generally what people do is add 1 to everything. So a frequency of 1 to overall to the model so that the denominator is never 0. Where we add the 1 is what the argument's over. I don't think I've practically ever had this change much for me, but it is a thing to be aware of. Okay, One reason I like it though is it's so similar to count vectorizer. That's why I can't get over it. So it's like it's so nicely programmed in how easy it is to kind of do a bunch of these. It's a pity that the math is not maybe the one that everyone wants it to be. So what do we do? tfidf vectorizer. Okay, use IDF. Okay, equals true. And then we've just basically set the same parameters as before with a minimum and maximum proportion. And then it's exactly the same as the count vectorizer, fit transform on your trained corpus, just transform on the test corpus. And we should see the exact same numbers because this is a normalization procedure, not anything like it just takes that same matrix and changes the numbers on the inside. So same basic output. Let's run through all three of those again. Okay. So I'm overriding my original model. I'm resetting my original model. Okay. Don't just do another fit because I'm never quite sure if that actually resets the model or not. I've looked up the documentation. Sometimes it says that it does, and sometimes it says that it doesn't. So I'm just going to reset. Okay, give me a blank model. All right, cool. Fit my data. Predict the data. Print the classification report. Wow, it looks very similar, right? But the accuracy on this one's actually 74%. So simply by switching from counts to weights, we went up 4%. But again, man, we just cannot capture this religion category. Just not doing that good. But where we gained was that basically all of the rest of these are in the 60s to 80s. It's this last one that's tricking us. Multinomial naive Bayes. All right. Oh, that's no good. It has the same problems as before. Okay. And it actually stays at 71%. It shifts around a little bit. Some numbers go up, but mostly the religion ones go down. So Bayes cannot capture religion, which is sort of hilarious if you think about, the idea behind Bayes and the person Bayes himself. But it does not capture these religion categories. What about SVM? Not doing bad, not doing bad. It actually went up to 76%. So SVM is now winning, okay, instead of Bayes, at 76%. So small changes here can produce somewhat important increases. Okay, it's what, 5%? 5% can be quite a lot. Okay, now let's look at what has happened. And I will tell you that the confusion matrix in the metrics part of scikit-learn is less than optimal. But if you want it in an array format, I think this is a NumPy array, you can do that. So that you can save it maybe in a pandas data frame and use it again later. But this doesn't mean anything to me and it doesn't print very well. However, scikit-learn is now on 0.24, but you need at least 0.22 to get this picture. Okay. So what you do is you do metrics.plot confusion matrix. You pick the one that you're interested in. So our SVM is our last one that did the best. You put in your test features. So here we've got our tfidf features. Then our actual answers, okay, our test label names. And then this, you can control a whole bunch of the way the plot looks, but I did vertical so that they're a little bit readable down here. I need to make the plot maybe a little bit bigger to capture all of it, but it gets us close enough. This is using matplotlib in the background, so we do plt.show, and then that's what will print out the plot. I love this thing. This color-coded beauty is fantastic. All right, what am I seeing? Down on the diagonal here, what we're getting is the correct answer. And so we want that to be the high colored colors. Right. Now, some of these categories are smaller naturally, but we want that's where the largest amount of numbers to be. And then I can start to look at the off diagonal, this kind of purpley area, to figure out where I'm getting it wrong. We've seen on all of these models that our religion categories were the worst. And if I start to look at the combination of the religion categories, you can see that I'm getting it wrong in a way that makes sense. Right? So our religion one, here's 15. Well, that's because it went to the atheism category. Okay. The 31 here, okay, is a high number in the wrong direction. It went to the Christian category. Oh, okay. That's getting it wrong in a way that makes sense. Now, into the guns category, that might make a lot of sense in the South, United States. You know, depends on where these things are. But I think if you weren't aware of sort of the cultural United States, that might not make a sense, but it makes a little bit of sense to me. So, yeah, I'm getting it wrong in a way that makes sense. Potentially, what I could consider here, since my religion categories are the most difficult ones to predict, is to combine them all into one overarching religion category, and then I might be better at getting it right. What we find is we don't have enough data to distinguish the three different ones, so we'll just collapse them together. You can see a similar thing here with sort of computer stuff, right? Graphics, if I get graphics wrong, it's because I'm in the Windows category. If I get the Windows one wrong, it's because of graphics or hardware. So this kind of cluster right here makes some good sense. We're getting it wrong in the slightly wrong category, or electronics. So these models, I would say, make sense. Okay, they're doing a pretty good job of prediction, and when they don't get it right, it's usually in a way that is a close neighbor. And then you might even pull out the probabilities to start to see if the probabilities are very close. All right, now this finally finished running. Let's see if that fixed our problem, our issue here. Oh gosh, where was that? Here? Ooh. No. So that still is mad. So I could keep running it, keep updating the number of iterations, or I could call it a wash. Because we don't have this problem with the tfidf, right? And that one is we already know is better. Okay. But always watch for these errors. Okay, it's something I teach in my structural equation modeling class too. It can be easy to miss them if you're running a bunch of code at once. Always make sure, because models that don't converge are maybe not to be trusted. If you were really wanting it to converge, you could keep updating the number of iterations until you get tired of dealing with it, or you can start to change some of these penalties, these normalization or regularization factors. But in our case, we already know we have a better solution. All right, thought we could try. Now let's spend the last little bit of time here talking about one more feature extraction. Okay. If you want to learn more about word2vec, there's another course, 540, that spends either a week or 2 weeks on word2vec, and then covers a little bit more into deep learning models. Not too crazy, but just a little bit. This is going to be a very fast, quick and dirty overview of word2vec. But it is a very popular type of extraction method, so I wanted to definitely cover it. Okay. And what the biggest criticism of bag of words models is that they don't handle context. Right? That's the entire point. Take the words and you shake them up in the bag. Okay. Neural net models are meant to deal with that. So I could move up to a 2-gram model or 3-gram model, but that creates a big sparsity problem, where the numbers in the matrix just get smaller and smaller, and we have less examples that may or may not be predictive. So the solution may be word2vec. Okay, I'm going to show you Gensum here. Fast text, remember, is Facebook's version of word2vec, which is originally developed by Google. And the nice thing about GenSum is you can switch between word2vec and fast text with like changing 5 or 6 characters. So you can actually test a couple of these types of simple neural net models pretty quickly as well, depending on how big your model is. But the entire point of a neural net model, right? So a simple or what's called a shallow model and our deep learning models is that they're meant to mimic the way that our brains work. And they have some amazing stuff that they have done with these neural net models. One of my favorite things that I talk about either earlier in this class or in the other class is the Google's zero-shot translation system is a very cool neural net that does some things that people can't do, right? But they're meant to mimic people. With this basic understanding of neurons. So neurons in your brain, right, they fire, something happens, there's a lot there that goes on, but they're connected together through these layers or these connections. And most of our experience is due to the patterns of connections, right? I don't have a neuron right here that's for apple. Right? I have a bunch of neurons that are about the shapes of apples, the colors of apples, the experience of apples. I don't know why apples today. Pizza if you want, since it's almost dinner time. But experience is a pattern of activation in the brain where the neurons are firing. And there's different organizational structures in the brain too, right? So we know that the front half of the brain tends to do abstract thinking, kind of working memory. Back half of the brain is for visual, small perception stuff, right? Kind of the middle here for auditory, to give you the very brief brain breakdown. And a neural net model is trying to capture this idea, right? So there are parts that we know what they do, and then there's plenty of brain that we don't know what the heck it does. And they're organized, they being neural net models, into these layers. So generally, a simple model like word2vec has an input layer of nodes that you turn off and on to mimic seeing something, hearing something, representing the inputs. They have one hidden layer and then an output layer that predicts what is related to the inputs. Those are connected via weights. Those weights are adjusted with training. And this is not a word model, but I just my best Google at simple neural net models. So this one's actually about cholesterol, right? But here's the idea. We've got an input layer, a fully connected hidden layer, right? Where each one of these arrows is a weight. The weight might be 0. These two things are not related. And then an output layer that tells you, predicts what should happen. Okay, sometimes you'll see it with a bunch of bubbles and it'll just predict one of the bubbles. And what that does is this hidden layer is meant to mimic the processes that are going on in the brain. Okay, and all the neurons that are firing that we don't know what they do. Now the hidden layer in a word2vec is trying to capture these kind of distinctions in context, okay, in one of two ways. So the bottom here would be our input layer. The hidden layer here depends on the type of model. And then our output for a word2vec model is actually always what word should come next, or the context of that of the words around it. Sorry, it's the word in the middle. So this particular model is a 5-word window, or I'm sorry, 2-word window, 2 words on each side. And so we're trying to predict the word fine. Okay. Fine is a complicated word, right? It could be I am fine, or in this case, fine leather jackets, meaning expensive. So we're trying to predict that context. In this 5-word window, okay, 2 on each side. Sorry, I'll try not to say this wrong. This is a confusing part of the documentation. When you have window size, it's the number of words on each side. Okay, so this is 2-word window, which means it's 5 words. 2 words in the front, the context word, 2 words in the back. And so what we see is selling these fine leather jackets. And the first option is a SIBO. SIBO models are continuous bag of words models, which what they do is they take in the window size. So here are all the words. and it averages across the other words. Okay, so it's the whole context taken together. And so you have to see all of these to get that instance. Okay? So it's essentially like trying to mimic this idea of reading where we like look at one word, but we actually see the little things around it. Okay? And that whole thing needs to happen for it to predict the context word here fine. And so it's creating these sort of average vectors of context. That's why it's across all of the words here. A skip-gram model still uses that same window size, but actually relates them one-to-one. So it says, well, if you see selling in the next couple words, you might see fine. Okay, if you see these in the next couple words, you might see fine, leather. Okay. So they're treating context differently. Here, this is more of a strict context where all of the words kind of get averaged. Their training or their tuning kind of averages across all of them. In a skip-gram model, they're one-to-one. So I would say SIBO models tend to be a bit more specific for context. Skip-gram models assume that context is kind of this fuzzy thing that gets moved around. But they're still tied to each word. So it's capturing context a lot more than bag of words. Now, to implement a word2vec in GenSum, it actually takes a corpus that has been tokenized. So the first thing we have to do is take our training data set, our cleaned up data, and tokenize it. The easiest way to do that is using NLTK's word tokenize. Okay. And so this takes what we had, which is a list of strings, converts this to a list of lists. And the reason it requires such is because it, in a skip-gram model, it's token 1 to token 3. Right? So that's an important distinction. You've got to convert your training data set into tokenized list, a list of lists. Now, there are many places to tweak these. These models are very flexible. You could spend days figuring out which one's best. Been there, working on it. So we'll import GenSum. And we'll say, okay, our word2vec number of features. I say 300. That's a slightly arbitrary value. You could go higher. I've seen many machine learning models where they suggest like outrageous numbers. You don't want to go higher on the number of features really than the number of words that you have. That would be a little weird. But essentially features here represent the size of the hidden layer. I picked 300 because in my previous readings of word2vec models in my own area, this has been a size that traditionally has worked really well for prediction. But I'm not attached to 300 saying that that is the answer. You could go smaller, you could go larger. So one thing that we've done is we've tested this 50, 100, 200, 300, 400, 500, 600, and we figured out the spot at which increasing the number of features here or hidden nodes tapers off. It doesn't add anymore. So that's one thing you can do. And we'll build our model, right? This one you don't build a blank model, you just build the model. So GenSum models word2vec. We put in our corpus. We put in the number of features we're interested in. Okay. Window size here, I should really lower this number now that I've read the documentation and talked to the creator of GenSum. If you ever have questions, they're very responsive on Twitter. It's really nice. But if you look at the documentation for fast text, it makes it sound like the window size is the whole thing. So if I set a window of 10, it's 10 words, including the target word. But if you look at GenSum, it says, no, it's the number of words before and after. And so I got in there and was like, which one are you doing? Which one is right? Is the number of words before and the number of words after. So this is actually 21 words, including the one in the middle. That's a little large, personally, because people can't remember 21 words. They should probably make this more like 5, which was the actual original intention, was a 5-word window on each side, but I thought it was the total number of words. So just FYI, learning from my misunderstanding of the doc. But we can do 5, we can do 10. You could test different versions of this number. So you can see quickly how this becomes a problem of trying a bunch of different models. Min count here is 2. So that's their suggestion is to use 2, but you could change this all the way down to 1. Now this is counts and not probabilities. So min count of 1 will keep every token. Okay. Min count of 2 just requires, this is not a good label, minimum number of times a word has to occur to be in the model for the vocabulary, is what this is. Skip gram equals 0. That makes it a SIBO model. I can switch this to 1 to make it a skip gram model. Okay. Number of iterations and number of cores. If you're on a Windows machine, you can lower this. That'll sometimes, if it hangs, it will help you unhang, basically. Cool. Let's see what happens. So we can tweak a lot of these features. We won't because we don't have full class time for this, but the problem with a word-to-vec model is, what do I get out of it? Because the entire purpose of a word-to-vec model is to predict what word is occurring in context. What does that have anything to do, right, with predicting the category? So in a deep learning model, you can predict categories, but in word-to-vec, right, we are really interested in context. And so the purpose of that model, the way it's set up, is to predict the context of that word. So what do I got to do to get out the data that I can use for prediction? And this was provided by the book, and I have used it several times. Effectively, what it does is it takes the vocabulary that you have, all the words that went in, and averages over their different contexts. And what you end up getting out, like all this stuff, is basically creating a complex average. What you get out of it is a vocabulary by dimensions matrix. And we put in 300 dimensions, so, you know, I could go much higher here, but instead of being documents, sorry, I've said a slightly wrong thing. What we end up with, is a documents by dimensions matrix averaged over vocabulary. Okay, so documents, because we're predicting the documents, right, by dimensions, 300. Before, we had a documents by vocabulary matrix. And now we've switched it to documents by context. So each of these columns, each of these dimensions now represents sort of an average context over our vocabulary. Okay. And that's really interesting because what that gives us now is more, I don't want to call it themes because that's more of a latent semantic analysis or a topics model, but it's given us sort of a different higher order representation of what's in the text. Before it was literally the raw text. You know, now this is more of a representation of context embedded into these dimensions. Okay. So these are called word embedding models for a reason. We're embedding the words into this hidden layer, but to be able to predict, we're taking those, kind of flattening them down. That's what all this bad boy does. If you're cutting and paste this, make sure you get the tabbing correct, or it will throw an error message. But once you get the document vectorizer function running, you put in your corpus, or tokenized train, and put in our model that we just built, right, and how many features we should be expecting to get back out. Cool. Does it work? Not really. So my basic log regression, I'm going to fit it. Now I've got my training features here from word2vec, and it's actually not very good. Oh, especially in the religion category. It doesn't predict religion at all, so it's only getting 50% right. But this is one word2vec model. I could say, okay, that's just not enough dimensions to capture how much is going on in the fact that we've got 3 different religion ones and 3 different sports ones. Maybe I need 10,000 dimensions. Okay. So I could run that model instead. So word2vec is it does take longer to find the search parameters in the sense of finding the right combination of dimensions and window size and skipgram versus SIBO. Okay, so this particular one didn't work very well. Question. Dimensions, there's 300 dimensions, and dimensions are meant to represent those contexts, those embeddings, and they're sort of averaged over every context in that document. So it's a representation of embedding. I don't want to say it's a representation of theme, but more of like what is in the document on a higher order. Because there are other types of models, again, that this is covered in the other class. Latent semantic analysis or topics models are very popular that are more like traditionally considered thematic analysis, where we're getting the themes from the document. Okay. But either way, it's kind of like a factor analysis. This is the latent structures that are embedded in context. Maybe I don't have enough of them to fully capture the differences in these different categories. Let's see if many of the other algorithms work any better. Okay, so I've got Bayes, and I really want to hit this point for Bayes. Bayes does not allow negative numbers because Bayes is all about probabilities, and it doesn't like negatives. So if you decide to pick this model for whatever you're doing, and you get an error message, it's probably about negative numbers. So what I did was I took my train features and I did .min, and then my test features and did .min, and I found the minimum, and I just added that number to each one. So I did a linear transform and just added 4 to all of them. This brings them all, it maintains the pattern of relationships and the mathematical differences between dimensions, but makes them all positive. Okay. By doing absolute values, we would lose the structure of the matrix where they have the same different scores, right? But by adding 4, we've just moved them all up. Okay. 4 is because the minimum is a negative 3.07. It's not a random number. It's based on this lower min. All right, and then I ran Bayes on it, and it's still just as bad. It's even worse, honestly. Can't get atheism or politics. So religion and politics, 2 things you don't talk about with family, right? It doesn't like that. Now, when you have a parameter that has an F-score of 0, it will give you a warning. Keep an eye out for that warning, because that means that you're not doing very well. Maybe you haven't done anything wrong, it's just the model's not very good. One last time, try again with SVC. We can see that this did not converge. I bet it wouldn't even if I ran it 10,000 times, as we saw in our other one. And this model's kind of all over the place. Right? And our accuracy is only 43%. So I think neural net models are really cool. I think they're very predictive sometimes, but maybe not always. And so this will take me back to a point I tried to make, I don't remember when, but when working with these models, one should always consider the complexity, the computational complexity of the model, because even if our word2vec model, let's say, got a 76%, the linear SVC on a tfidf is computationally much faster. And so there are times when I'm not clear that adding context, it seems important, right? So our bag of words models don't include context. Well, we're losing all the information about sarcasm or about word meaning. And word2vec is meant to capture these shades of meaning and deal with polysemy, right? But sometimes that added complexity is not worth your trouble. In this case, very much not worth it. Now, I should play with my parameters and see if the skip-gram model works better. Should the window size should be smaller, maybe for smaller amounts of context, and maybe the dimensions should be much larger. So I'm not saying it's never useful. I'm saying that I think to move into neural net models, because they often can take a long time to run, there should be a clear added bonus for that complexity. If log regression will do the job, use the log regression. Just don't do the deep learning model just because we're enamored with them. All right. So in summary of all of the 2 weeks, okay, we've examined 3 different options in classification. We've actually 3 different feature representations: a straight count vectorizer, which could actually be a one-hot, right? We did the regular counts. We did the tfidf normalization transform on that, and we tried a word-to-vec model. We also did 3 different algorithms: log, Bayes, SVM. There are many more. So you can see how this can become a problem of finding the right search space. Okay. My votes start with the simple ones, then work more complex. Because if the simple ones will work, great. Move on. And what we see by looking at our results is sort of proof of concept. The features do have an impact on the outcome. Okay, tfidf seems to work the best here. And the algorithm also has an impact on the outcome where, and there's an interaction between the two on prediction. And so classification can be a little while to figure out and tweak until you find the right set of parameters that work for your model and your task. That is classification. What we'll start next week is sentiment, which is a special classification problem. But we'll also cover unsupervised models because there are some really quick and efficient ones. We'll see how good they are for sentiment analysis especially. All right, questions?